Today is our final day on Chapter 28. We're closing out our discussion on basic circuits. So, as we have seen it so far, we've been talking about batteries, we've been talking about resistors, we've been talking about current flowing through them. We've talked about capacitors, but a lot of our time has been spent talking about aspects of capacitors and not necessarily anything that they're actually used for. Right? Not how they're used in real circuits. What we see in this diagram right here is what a real resistor in a circuit might look like, or at least the inside of one. Here I have in my hand another one. This is a pretty large one, as you can kind of see. I know it's a little bit difficult to see on this one, but that's about the size of a large capacitor, for example. But it's the same shape. A lot of these are like cylinders, more or less, and the inside of them might have a little bit of variance between them. Sometimes they are coiled up plates. Sometimes you'll see like what we've got in our background picture right here, where it's fins that are laid on top of each other. And I've got a fin that has one charge, and then there's like an electrolyte infused paper acting as the dielectric in between. And then your other plate. And the entire reason, remember, that we had dielectrics in the first place was to increase the capacitance so that it was a reasonable size, right? It's this and not the size of my notebook to get effectively the same capacitance. So, today, we're exploring those a little bit more. So, up until this point, we have continuously seen resistors acting in circuits, and we have been in a lucky kind of position that these have been relatively simple. If I close the switch on the circuit that we've got up here, current is going to run through that resistor, out of the battery, into the resistor, back into the bottom into the battery, and the current should be a constant value the entire time. Right now, realistically, sometimes batteries die once they're used for a long time, but for the most part, if we ran this thing for an hour, for example, we would probably still see a pretty constant current the entire time. And that'd be fine. No crazy things would happen. But what happens if we put a capacitor in there too? Think about what this might mean. If I am looking at this capacitor, if I just look at the diagram, what do we see? When we close that switch, can current flow through the capacitor? Well, there's a gap, right? There's no wires connecting these two pieces. With the gap in between those two plates, and whether they're fins or plates or whatever, but the idea is that when there's a gap between those two, charge can't actually move between those. So was there any current to move at all? And I pose this question, but we have already seen some hints as to what happens. If you remember, we had one whiteboard problem that we did together where we had two conducting spheres. And one of them had a potential on it, the other had zero potential. And we said, okay, now we connect them with a wire. What happens? Does anybody remember what happened in that problem, though? What was our final state? Yeah, and it wasn't quite that the charge evened out. That was the trick. It wasn't that the charge evened out. It was that the potential evened out. Remember that it's a potential difference that moves charge. You need to have some sort of potential difference. It doesn't matter if it's at very high potential or anything else. If one of those conducting spheres was at 200 volts, but nothing ever connected to it, it's going to stay at 200 volts, right? It doesn't care. It's fine that it's at 200 volts. And that's, I think I've talked about this a few times when you're walking away from down power lines, stuff like that. It doesn't matter what the potential actually is. The potential being a certain quantity is not a big deal. The thing that's actually going to move charge is a potential difference, a high and a low. When there's a high and a low, that's when charge will want to start to move. So, in that case, we saw from a bunch of, from a high potential location to a low potential location, charge moved. So maybe there's more to this. Maybe there is some motion going on. And as we get into that, if you have looked already, the questions that we have for the day are done through mastering. And I didn't realize this at the time, actually. I was under the assumption that they had fixed this up. This particular simulation doesn't run in the browser. And I swore it did. So I'm very upset by that. I don't know why it isn't running in the browser. But in any case, I've got it set up here so that we can actually look at this thing. So I'm actually going to reset. Let me reset this entire thing. Let me reset this entire thing and we'll start to take a look at these. Let's get rid of this thing for now. Get rid of this. Get rid of that. Okay. So I'm just going to go through, and because you've got to run Java on your computer to have this done, and I'm not going to assume that everybody does this. If you choose to, Windows or Mac will throw up a little bit of a fit to say it's unverified from, you know, code running from the internet. Be warned, and it's not a worry at all, I promise. Pearson is using it. It's from University of Boulder, funded by National Science Foundation. It's completely safe as a program. Windows is just scared of things. If you choose to run it yourself, but I'm going to run it here for you guys anyways. So let's go ahead and look at these questions though. Let's go ahead and pull this up. So in order here, and I'll make sure, yeah, we can see all the steps. So we're asked to set up this sort of circuit to begin with, right? So here's our battery, our resistor, a switch, and a capacitor. Let's set it up. A resistor, a switch, a battery, and let's put our capacitor down here. And we'll just set all these details up real quick. Bob Ross style, the happy little capacitor in the battery, something like that. Anyways, so we've got this thing hooked up, and the switch is open, the circuit is open, there's nothing going through, right? But let's watch what happens as soon as I close the switch. So we just saw a few different things. The capacitor certainly didn't have that fun little texture when we started, right? It was completely blank, like what we see on the right side panel here. There's a little bit of current that actually moved, right? Not now, of course. You know, these things are clearly not moving now, but in that brief little moment, there was some current moving. And let's think about why for a minute here. And I'm going to pull out my voltmeter to try and help me describe this. What we saw from that problem that I was talking about before, the problem that we have seen in the past. If you remember, it's that when we have a potential difference between 2 points, charge will start to move. So when I close this switch, my capacitor started at 0 volts. There was no charge on it. The positive end of my battery, let's measure it, starts out at 9 volts. Now, AA batteries are only technically 1.5 volts, but we'll forgive them for this one. 9 volts is pretty standard. So it only had 9 volts to begin with, but now what we see is that the charge moved until this entire pathway, if you watch as I move this probe around, so I move it off, it's back to question mark, but as long as I'm on this wire, this entire path is all at 9 volts. The potential difference has gone away. This entire path, the top path, is equal potential the entire time. And that's what made the charge move. Let's go ahead and reset this real quick and look at it. Watch that voltage go up. It started at 0. And it continuously rose until it hit 9 volts to match the battery's potential. And at that point, there's no potential difference. There's no reason for the charges to move. What about the other end? Well, it's at 0 technically, right? If we're calling this 0, remember that it's one of the potential differences are the most important part. But that's what we end up getting here. And this is kind of an interesting idea, that when we plug this thing in, the entire circuit, or each end of the circuit rather, because the battery is not a continuous kind of deal, we see charge moving through it, but it's providing that charge in the first place, right? So if it's providing that charge in the first place, it's not really acting as a pathway for the charges to move through. It's providing those charges. One end of the circuit is all at the same potential. The other end of the circuit is all at the same potential, but those two potentials are different. They match the potential set out by my battery, the 9 volts. So if we're looking at our first question here, and unfortunately it's going to keep saying that these things are answered for me. Is that a second one open, or is that just something weird just happened here? Here we are. So when we're asking about this, now close the switch and monitor the resulting current through the circuit. After the switch is closed, there is initially a current, but it decreases with time and eventually stops. Once we hit that same potential as the battery, no more charge can move. So the second part of this, long after the switch is closed and the current becomes very small, what is the voltage difference across the capacitor? It matches the battery. And that's the only answer that makes sense, because anything else would mean the charge is still moving. So, going into part C here, repeat it several times and start changing some of these values. So let's go ahead and pull out one of our graphs here. Let me get my current chart going on here. And let's line it up right here so we can actually measure it. So we've got 0 current currently. Slight pun, not intended, but there nonetheless. Let me reset the dynamics and let's watch what happens. Does that answer make sense? Does that behavior make sense, that it goes all the way down to almost -1 and then slowly rises back up to 0? Why might it be that we have the greatest current at the very beginning? And that's an answer, or that's a question for chat. What do we think? Why might it be that the current is greatest at the beginning as soon as it's closed? Why isn't it even the entire time? As the capacitor charges, it's harder to put more charge on it. Remember, it's the potential difference between 2 points that actually makes the charges move. And the greater the potential difference, the greater the electric field, the greater the force. As the capacitor becomes charged, as it picks up that potential difference, there's a smaller potential difference between the positive end of the battery and the positive plate of the capacitor. It starts out at 9 volts, and it gets smaller and smaller and smaller as time goes on until we approach 0. At which point, no more charge can move, but at the very beginning, we have the greatest current because there's the most force sending the charge along their way. Now, and this is kind of an interesting thing, because this is something that we have so far neglected. But the reason that we can do this in the first place is because, well, yeah, we've got to move this potential around. Why haven't we seen this with wires? Technically, it's there too. But in comparing the capacitance of the wires to the capacitance of, well, a capacitor, it's very, 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 very minimal when you're trying to compare these two. For example, if I disconnected this real quick, let me go ahead and split this junction. Let me pull this thing out real quick. We still read that this is at 9 volts. The wire has still technically picked up this voltage. We just assume that the capacitance is 0, but realistically it's a vanishingly small capacitance. But there is a capacitance. And in real circuits, sometimes that's an issue. Especially when we're getting to much, much larger circuits, like you might expect to see in something like a power grid. Right? At that point, the capacitance of wires is something that really actually matters. So anyways, let's reconnect this thing real quick because we've got a couple more points that we wanted to look at. So let's read that value one more time and watch what happens. So we dip down to -1, and then we're going from 8205 to most of the way there at 8207.5. Okay, so now let's change some values here. Let me ramp up the capacitance. Let me take this all the way to 0.2 farads. Reset the dynamics. What we see is we went down to about the same current, I think we can all agree, but the time it took to get all the way back to charged, and still, You can see it's still going, still going, still going, still going, still going. There it is. Takes a much longer time to get back up to 9 volts. And why is that? Well, there's a lot more space for all of these charges to be. There's a lot more surface area for the charges to be resting on somewhere without colliding into each other nearly as much. So there's a lot more charge that needs to be moved. But now let's see what affects that rate of flow, because we just saw the time it takes, so the flow rate doesn't necessarily depend on the capacitance, at least the magnitude of it, but the time it takes to stop the current does change. Let's see if we can do anything to that -1. What if we change the resistance? Let me double the resistance to 20 ohms. So I've now made the pathway to get there a little bit more difficult. Now we see we only hit about half of the current. But it still takes a really long time, right? It's going to take a really long time. What's happening here is that both of these factors are affecting what's going on with my circuit. In the case of resistance, that's stopping my current from moving there in the first place. So it's going to take longer to actually get to the capacitor, and it's going to kill the maximum current that I could see. By increasing the capacitance, the capacitor is at the start, not trying to interrupt that flow of charge. As time goes on, though, as it gets to a higher and higher potential, there's less charge that can actually be moving around onto these things, and it's going to slowly decrease down. But those are the two factors that we see here that might be affecting things. So when we're looking at this problem as it's given on mastering, repeat the experiment. The amount of time increases if the resistance is increased, and the amount of time increases if the capacitance is increased. Both of those things are either slowing down the flow of charge or increasing how much charge needs to flow to fully charge up the capacitor. So both of those things would be increasing the amount of time. That doesn't say anything about the current, the maximum current, but the amount of time it takes to fully charge the capacitor. Now, we've got one more here, and we're setting up something a little bit different, and this is a really cool one. So let me go ahead and set this up. Let me just reset everything real quick. Let's make a new one here. I'm going to move this thing over for now. What I'm going to have now, I've got my battery. I'll set up a little resistor. Let me put the switch right here. Now I'm going to have two different paths. One path goes to a capacitor, as we have seen so far. Nothing crazy there. And let me take this down just a little bit. We'll give ourselves a little bit more space so that we can see this thing. So there's our capacitor portion. And now the other part that we're going to add is a light bulb. And I want to make sure that we've got space to look at this. So let's go ahead and do this like that. If you'd like to play with this one a little bit yourself, I do recommend it. It is a lot of fun, but it does... This is the older version, the one that you just used for the parallel and series. It has a lot of the same features, right? All of these similar things that we've seen from last time, including the dog for some reason. They were just dead set on that one. But it does have some neat features that the newer one doesn't, unfortunately, which is why we're still using this one. Okay, so before I flip this switch, what do we think is going to happen? What's going to happen to this system? Take a guess. We will charge the capacitor, but I'm most interested in what happens to the light. Yeah, let's see it. Let's see what happens. Close the switch. There it is. The bulb is at maximum brightness. Let me go ahead and reset that one more time. So watch what the bulb does. Starts out very dim, gets brighter and brighter and brighter. And why would that be? Well, if we actually look at what's going on here, in the very first instant that the switch is connected, so the battery and the capacitor are connected together, there is no potential difference over that capacitor. And for that brief moment in time, a zero potential difference means that there is no difference between the capacitor being there and just a plain old wire. The picosecond after that, or the femtosecond after that, that some, instantaneously, as soon as we hit that, now it starts to go back down. Because now there is a potential difference because of this, and that slows down the flow of charge. The light bulb, on the other hand, so at the very beginning, this thing is acting like a short, right? It's acting like a short right between those 2 points. As time goes on, because current through the capacitor becomes impossible, current along that path decreases down to 0, now all of the charge is forced to go through the light bulb instead. So this could be a fantastic little thing for a charging indicator, for example. Right? When the battery is providing that strong voltage, when everything's all set on your capacitor, maybe it doesn't have any current anymore and the light turns on. But in any of these cases, here's what we've got. Now, that isn't quite the answer to the problem, though, because what we're asking here is to set this thing up, build the circuit shown in the figure. What happens to the luminosity of the bulb when the switch is then opened? What do we think? I'd love to see some guesses on this one. What do we think is going to happen? Is it immediately going to go out? What happens here? Let's test and find out. Whoa, that's not the right thing. So we disconnect it, and immediately we see it doesn't go down immediately. Let me go ahead and record. Let's record what happens to the current as time goes on. So right now we've got a current going through this thing. I open the switch. It doesn't make a discontinuous jump, right? It's still a continuous function if you remember all of those early calc terms. But it does certainly start to decrease. We reconnect it again. It ramps back up. But you can see even then, when we reconnect it, it quickly jumps and then it slowly fades to the running current that this thing would experience. And let's kind of prove my point one more time. So if we're thinking about what I had just said about it acts like a short for a little while. If we have a short in the system, what are we expecting the resistance of the system to do? Not necessarily 0 all the time, but certainly much lower than it would be, right? A lower resistance would then mean a higher current. Let's try it. Reset the dynamics and let's see what happens. Yes, indeed. Our current briefly spikes because the resistance of the whole circuit has gone down, and then it goes back to its normal value. And then we open this one more time to just see what happens to the light bulb. And this is kind of an interesting feature, right? Because this is actually a pretty important thing. Capacitors are very, very cool because they introduce a factor of time dependence to all of our circuits. Whereas resistors were just constant with time. It didn't matter whether you looked at it now or an hour from now, it'd be the same current. Capacitors depend on when you're looking at them. They depend on that time. And this kind of feature actually is one that is probably in use right now in your house where you see this fade to 0. A lot of surge protectors come with tiny capacitor banks inside of them because the general idea here is that a sudden cutoff of power can hurt certain electronics. It's not good for electronics to suddenly lose power. But a lot of surge protectors will introduce, for one, a voltage regulator inside of them. So it dumps extra current and voltage so that they don't overvamp and destroy any of your electronics, but sometimes they'll also have capacitors inside of them. And the entire point of the capacitor is to rapidly ramp down that potential so that it's not just a sudden cutoff of the power. It's got a little bit of time and that, it's a rapid decrease, but rather than being a cliff, it's a very, very steep hill. And that's oftentimes enough to just help save electronics from getting damaged. But it's a neat thing. There's all sorts of cool things you can do with this. You can tune all of your systems with these capacitors. Capacitors get used all the time for different things that have frequency dependencies or anything like that, oftentimes used as filters. Depending on which capacitors you use and the configuration of those capacitors, you can use them as filtering out something from an electric signal. And that's a really cool thing. Like a lot of my electronics boxes in the labs, oftentimes we would attach very large capacitors between the different potentials. So if we'd have plus 15, 0, and minus 15, we'd attach capacitors between them, because that way any brief fluctuations from our power supply would get evened out by the capacitor, just like what we saw here. So our final answer when we're talking about this part down here is that the luminosity is initially the same because it's initially providing the exact same potential difference. But as time goes on, the current fades down to 0. So, capacitors are kind of cool, right? As we have seen in this a little bit now, we've got some neat things going on. When I'm charging up capacitors, we actually have this old equation that we haven't used in quite some time now, but it's our old equation that the potential difference on a capacitor is equal to the charge on the capacitor, or on one plate, divided by the capacitance. Once the switch is closed, we're going to see that the charge, the current, the potential, all of those things on a capacitor gain a time dependency. So the trick here is, what are those time dependencies? What do those equations look like? And in the meantime here, I am going to switch over to a slideshow actually, so that we can look at these pieces and I can talk about these. What we have to do is we have to handle this with a loop law. So if we've just got the capacitor and we've just got the resistor, let's handle it just like that. So if we draw the loop here, we get a potential difference because of that capacitor, right? The delta V of C is the potential difference because of the capacitor. Minus IR because we're going with the current through the resistor, that kind of deal. We remember that the potential difference on a capacitor is just the charge divided by C. Now, this has been a little bit of time since we've looked at this definition, but we might also remember that current is the rate of change of charge. We said I is equal to dq dt. Now it's a negative because it's charge flowing from the capacitor. So on the capacitor, leaving the capacitor, which means it's going to be a negative dq dt in this case. If it was a charging capacitor, then it'd be a positive dq dt because that'd be charge moving onto the capacitor, but this is charge moving off. So let's take those two things. Let's take our definition of delta V, let's take our definition of I, let's plug those things into my loop equation, and I get something that looks like this. Q over C plus R dq dt. And you might recognize this as a differential equation. Now, I'm not expecting you to know how to solve a bunch of differential equations right now. Some of you might already know. Some of you might have taken a class or are currently taking a class on these things. And if you have, more power to you. If not, that's no big deal. This is not any sort of crazy calculus that we have seen. This actually looks a lot more like what we have seen so far. I have dq over q. If I integrate that, what does that turn into? If I have 1 over rc, which are both constants, by the way, and I need to integrate dt, what's that? The trickiest part is actually thinking about our bounds. If I integrate q, I want to go from what q I started with, how much charge did I start with, to however much charge I have at the end of the day. And let's say that I close the switch at 0 and I'm trying to figure out what this thing looks like now some number of seconds later. Then I integrate both pieces and I get a natural log of q, because 1 over q, the integral of that is natural log, is equal to negative t over rc, because integral of dt is just t. Plug in our values. And I know this down here is just from 0 to t, is what that's saying. So you're not missing anything on that one. It's just the same thing as we already saw in the bounds. Now, as we've got this, oh, that one is cutting off a little bit though. This is q over q naught is equal to negative t over rc rearrange this whole thing a little bit because I don't really want to deal with that as it is. I would much rather think about this equation right here. And there's nothing else on the side that I'm cutting out. You're seeing the last bit of it. This rearrangement is very interesting, though. If you didn't recognize at the beginning, what we have now is an exponential decay of the amount of charge on the capacitor. And that kind of makes sense if we start to think about it, because anytime we start to see an exponential decay or an exponential growth, it's always because something is constantly changing in quantity. It's an exponential that's constantly changing based on the current value of that exponential. Based off of that initial charge that we had before we closed the switch. Which then means, let's extrapolate this a little bit more. If we know that the charge is constantly changing, that should also mean, if we go back up to here, that the potential difference over the capacitor is also constantly changing. Which makes sense now. We've seen this, right? Because we saw what happened with the light bulb. When the switch was lifted, when the capacitor was the one providing that potential difference, we saw the current and the potential go down. So we can take it like this, and let me go back out of this now. I don't want to keep those ink annotations. Let's go back to this so we can actually see this. Here's our big equation, right? Highlighted now in red, what we just found on that previous page. We're going to call this value RC our time constant. And this is a little bit of a tricky thing because ohms times capacitance is not necessarily seconds, but we're saying that it's equivalent to these two numbers. If I put these two numbers together, I'm going to call that tau, and tau is what I'm going to now refer to as my time constant. So when I plug all of these things in, right, and here's my argument about taking Q and plug it into delta V and then plug it into our circuit, we find that not only does the charge have a dependence, e to the negative t over tau, but so too does the current. In the exact same relationship, in fact, right? E to the negative t over tau. Both of those, depending on that initial value that we started with, and then decays down from that. Now, if it's been a little while since you've looked at exponential equations, this is the kind of graph that we're expecting to see. By the time we hit 1 tau, we are down to only 37% of our initial value. That is, once we hit tau, the current or the charge is 37% of what it started with. And then it just keeps going down from there. And that's also why we see this very, very long tail, that very long time to go from 8 to 9 volts, whereas the first 1 through 7 were instant, right? Or very nearly instant. So, do we have any questions on any of this stuff so far? If it's exponential, it means that it never will truly reach 0, but at 99.99999% of the way, I'm willing to call it. Which is why every single problem that we've looked at so far with capacitors has specified that after we wait some time. Because we're waiting enough time so that that decimal point becomes way far out and we don't actually have to worry about it. Okay, so let's look at a problem here. And this is a fantastic circuit, by the way. This is a great way to quickly charge a capacitor and then discharge the capacitor. Just switching back and forth between A and B. Because once we switch over to B, the battery is no longer in the circuit. Currently, the resistor is not in the circuit because there's no path here. There's an empty space. So don't necessarily try this because without a resistor, there's nothing to stop the current and you might cause the capacitor to explode, but let's not worry about that too much yet. What we're looking for are the charge and current through the resistor after it's been charged, and then we move this switch over to this position. Battery's disconnected, now it's just the capacitor and the resistor. Find the current and charge as soon as it's closed, 50 microseconds after, and 200 microseconds after. All right, so I think we should start to take a look at this one. So let me go ahead and steal this thing. we'll put this, let's find a good spot for this. And one of the first things I'm actually going to do here, that's a good size. I'm going to say, okay, we switched this thing so that it's now over on this side. Right? Now we've connected this side over here. So what I'm going to do, I'm just going to erase this whole thing, right? But, well, let me take one more step back. Let me mark this thing. So we said, okay, positive end over here, negative end over here, 9 volts right here. Now, battery, you've done your job. You're out of here, right? Let's just focus on what's going on the right side of the circuit now. So I'm going to erase all of these details, no confusion whatsoever. We are only worried about what's going on over here. So now, when we start, I think I've brought up this comment before. Capacitors are just really bad batteries. And it's not because they can't provide the same potential difference, it's because they don't keep providing that same potential difference. But if we're not worried about how long it can keep providing that same potential difference, then what we can do is we can focus on the fact that this is a potential difference and a resistor, and we can solve the current based on that. I'm going to start by solving everything out from the current first, and then we'll look at the charge later. So I know at the very beginning, I've got that 0 is equal to delta VC, the charge or the potential difference on the capacitor, minus IR. Delta VC is equal to 9 volts. R is equal to 25 ohms. That means our current, delta VC divided by R, is 0.36 amps. Whoops. And what I'm doing for today, because I think there's a little bit of confusion with some of these equations, I'm doing my units in a light gray. Just so we know that it's not a variable, it's a unit. 0.36 amps. Now, I need to specify, this is my current at the very, very, very beginning. The instant that I close the circuit. And this is important to get this one right because these other values as they follow will depend on this. Because we might remember, I know it's only been 10 minutes, but we might remember here that the current at any point t, after we have closed and allowed the capacitor to start discharging, is going to be equal to I naught, the very same, times e to the negative t over tau. Where tau, our time constant, is equal to r times c. And this has to be in standard units. Keep that in mind. We got to be careful with this thing. Well, it has to match the units of our time. So if I were to plug in these values right now, this would be 25 times 4 times 10 to the negative 6th. 4 times 10 to the negative 6 being our capacitance, 25 being our resistance, which means that this value, all put together, is 10 to the negative 4th. 10 to the negative 4th seconds is the strange unit of this. So now what I'm going to do is I'm going to say, okay, I know what I naught is. I know what tau is. I'm looking at two different points. The first, where where t is equal to 50 times 10 to the negative 6th, 50 microseconds. I'm just going to plug in all those values. That should be a negative t over tau. If I plug in all of these values at this point, then what I should find at the very end of the day is, and I had this somewhere, what did I do with it? There it is, 0.2184 amps. As my value for the current at that moment in time. Now, one of the other things that I could do for this to make this a little bit easier to deal with actually, and I have kind of skipped this step, we are given a time in microseconds. We could have converted tau to microseconds. We could have also said that this is equal to 100 microseconds, and that would have been fine. Then we would have just had to plug in 50 over 100, but it's a little bit safer right now to just make sure that everything is in standard units. So that's what I'm going with. Now, the exact same deal. When we're looking 200 microseconds, and I'll just put 200 microseconds. Now we're going to plug in all of those same quantities. We've got a new T, but the same tau, the same I naught. We plug in all of those values, and we should find at the very end 0.0487 amps. And those are our currents. Now, I said we were going to do currents first and then charges. So let's do that. Let me draw a squiggly line here. So the first thing, when we start, even before we close this circuit and we allow the charge to start flowing through, even before that moment in time happens, we have our initial charge, right? We have our initial charge Q. Because we had this old equation that said the capacitance is defined as the charge on a capacitor divided by the potential difference acting on that capacitor. So rearrange this real quick. Say Q is equal to C times delta V, and that's delta V of C, as we've got on it. Capacitance, 4 microfarads. Delta V, 9 volts. Plug those two values in together, and right off the bat, we should find something like 3.6 times 10 to the negative 5th coulombs. And in just the same way as I had with my current, I'm going to call this Q naught. This is my charge when I start this whole process. So now we're going to go through the exact same steps. If we remember what that equation looks like, Q of T is equal to Q naught e to the negative T over tau. We already found tau from the last part. Now it's just plugging in with Q naught. In this case, when Q is, or rather, when T is equal to 50 microseconds, we plug in all of our numbers, what we should find, no matter which way you do it actually, 2.184 times 10 to the negative 5th coulombs. When the time is 200 microseconds, (4.87 times 10 to the negative 6th coulombs. And there we have it. We just got a little bit lucky this time. It doesn't always turn out that these numbers look the same, even though the order of magnitudes are different. It's because we've got a 4 and a 25. That won't always be the case. If they're like 4 times 25 is 100, gives us that factor kind of 10 difference here. If we had this as 3 and 25 or something, you wouldn't see the same numbers anymore. Be a little bit different. But that's what we've got. How are we feeling so far? Are there any questions that we've got or anything like that? Okay. Since I'm not seeing anything, let's go ahead and keep jumping right along. So I've got another one here. And it's just a little bit different. Same concepts, still a discharging capacitor. But now we start with some charge on the capacitor, and then we connect it so it starts discharging through this resistor. We're looking for what resistor do we have to put there so that 2 milliseconds in, we're left with only 10% of the charge that we started with. All right, let's go ahead and start taking a look here. So I'm going to carry this picture over with me, even though we don't necessarily need it. It's not a big deal to have it because we're only going to kind of briefly use it. I don't need to actually draw a bunch of pictures on this one, which I know, shocker, but let's go ahead and take a look at it. The values that I do need to worry about are the fact that, for one, my capacitance is, I've already forgotten. I did this last time too. 1 microfarad. I keep getting the order mixed up of which one it is. So this is 1 microfarad, so 10 to the negative 6th farads. Whoops. Units in gray, please. Farads. We said the time is 2 milliseconds, so 0.002 seconds. Make sure that point's large enough to see. Now, here's the last issue. 10% of the initial charge. So Q of T is equal to 0.1 Q naught. I don't know Q naught. I can't solve this equation right here. That's, we're stuck in the water. But just for the fun of it, let's write out the capacitor equation anyways. A discharging capacitor has a charge on it. Q of T is equal to Q naught times e to the negative t over tau. We're looking for the resistance, which I remember that the resistance would be found, if I'm looking at this whole equation, the resistance would show up in tau, where tau is equal to RC. Do these two equations look anything alike? Is there a similarity between these that I might be able to pull out and use to help me? Why, yes, there is. What I can really do here, and what this is effectively doing, is replacing, I'm subbing in for QT. 0.1 Q naught is equal to Q naught e to the negative t over tau. The Q naughts go away. I'm left with 0.1. And I know that might have been an extra step. You might have been able to skip down to this one. But either way, I just wanted to prove the point. E to the negative t over tau. Okay, well, I'm going to have a really tough time algebraically solving something that is in the exponent. So what I'm going to have to do is I'm going to have to take the natural log of both sides of this equation here. So natural log of 0.1 is equal to the natural log of e to the negative t over tau. Anytime I take the natural log of some exponent of e, it just becomes the exponent, which is very useful, right? So this is going to become negative t over tau. Natural log of 0.1, on the other hand, I think I remember this number, but I want to make sure that I'm not goofing it up, should be negative 2.303. Both of those, I can get rid of the negative sign. Who cares about that thing? Now that I've gone all of this way, it's probably a good time to replace tau with my RC definition, but for now, it's simplified just a little bit. So what I can do is I can say, okay, well, this is now 2.303 is equal to T over RC. Solving out for the resistance, go ahead and move it over. Divide by the other thing. The resistance at the very end of the day should be equal to T divided by 2.303 times C, which should give us a final resistance of 868.6 ohms. And that's it. Let's go ahead and keep looking at things. So, what about the reverse scenario? We keep talking about a discharging capacitor. What about a charging capacitor? Well, it actually has a lot of the same features, and we've seen that actually. But things are just a little bit different now. So let's imagine that we're in a similar kind of circuit again. So we've got a battery, a resistor, a capacitor, something like this, right? Just in this scenario, for all of these things right here, if I am talking about the charge, I would take the curly E of the potential, or of the battery, the R and the C. Between all three of these values, I find a lot of similarities, actually. Because even like this right here, I can rewrite as I naught. All of these things are set in certain ways. The reason that some of this can be a little bit funky, because if the capacitor starts like partially charged or something, stuff gets a little bit different. Technically, curly E is the potential difference between the battery and the capacitor as soon as it's connected, but that's not going to be a case that we see very often. But there's just a few slight differences here, right? We notice that, again, towards the beginning, we see the greatest change. And I'm talking about all three of these. We see the greatest change right at the beginning because the potential difference is the greatest. The current looks exactly the same, right? As when we were talking about the discharging capacitor, the current equation has actually not changed at all. It's still just about exactly the same. The real difference here is that it's going now in the opposite direction, right? It's going onto the capacitor rather than off of the capacitor, but in either way you look at it, it's when you've got the greatest potential difference that you get the greatest current, and it decreases from there. When you have the greatest current, you're moving the most charge per second. Your rate of change of the charge on the capacitor is also at its steepest. And then finally, the potential based on that follows the exact same relationship as the charge. But all in all, the equations are really similar, right? So it's not quite reversible, but it's very, very similar. Now, one other thing that we had actually skipped in the meantime, this would have shown up in one of the previous chapters, but we skipped it at the time because we didn't really need it. But just like with resistors, we can actually combine capacitors just in the exact same way. They're just flipped. They're a little bit different because realistically, if I'm looking at like my bunch of capacitors in parallel, what am I doing? We can kind of see it. If we fill in the gaps a little bit, when I take a bunch of different resistors, or not a bunch of different resistors, the thing that I'm talking about, a bunch of different capacitors, and I put them all in parallel, I have effectively created a really big plate, right? That's all I've really done. If I've created a really big plate, the plate size means a larger capacitance, means that we're expecting to see this one is the one that increases. Parallel capacitors sum together. Capacitors in series, we run into this issue where there's some current building up, or there's some charge building up on this side, so it's negative on this side. And then this negative charge has to come from over here, but because it's a distance away, it has a tough time pulling it, and, you know, kind of onward and onward. So when I put capacitors in series, that's when I get the reciprocal sum instead. Right? So capacitors are strongest when they're put in parallel. Capacitors are weakest when they're put in series. The exact opposite of resistors. Now, one last point. This entire time, we've been looking at, let's be honest, pretty simple circuits. When I keep talking about the resistance and the capacitance, I'm not talking about these individual components. Technically, that's true here, but what I'm talking about is the capacitance and the resistance of the circuit, not just any one component. That's important because if we look at this problem right here, I can't just plug in 2 microfarads and call it a day. I have to take the effective capacitance of the circuit and the effective resistance of the circuit to properly describe what's going to happen. So let's take this problem right here. Let's say that the capacitors are already charged up all the way, and we are about to close that switch and start discharging them. But that's not really important what that is. I'm much more interested in finding the time constant of this circuit. All right. So how's about where we start taking a look? So I'm going to steal this thing over real quick, and then I'm immediately going to redraw this one. I'm not even going to draw on this picture, necessarily. So let's go ahead and move this thing over real quick. Shrink it down just a little bit. And then, what we said, what we said is that we don't actually care about what any individual component is doing in the circuit. What we'd much rather see is some way to reduce this thing down so that it looks like this. One capacitor, one resistor, the equivalent capacitor and equivalent resistor to the rest of the circuit. So what that means is that we will start with the capacitors. I have two capacitors in series, and in series capacitors is the reverse of resistors. Should look like this. Now, there's more than one way to do this one, right? Like depending on where I transfer units and everything else. But my hesitation here is that each of these are 2 times 10 to the negative 6th. And any fraction over 2 times 10 to the negative 6th is not very fun. You know, it'd be a lot easier if we didn't change that unit. If we just left it as microfarads for a little while, and that's fine. Because as long as C1 and C2 are in microfarads, I just have to remember that the equivalent capacitance is going to be also in microfarads. So let's do that real quick. What would that look like? 1 over C is equal to 1/2 plus 1/2. And I know my arithmetic has been really bad this past week and a half, but this is still one that I can do. What we find from here is that the equivalent capacitance is just 1 microfarad, which we can then say, okay, let me put that back into standard units. 1 times 10 to the negative 6th farads. Light gray farads. So we've got one of our values, right? Now we just need to do the exact same thing with resistance. Luckily, these two resistors are also in series, which means that we are just plugging these things in together. Summing them all up, the total resistance when we plug this in is 2,000 ohms. My time constant tau is just equal to R times C in standard units. That would give me 0.002 seconds. Or we could convert this to 2 milliseconds. And there we have it. That's it. How are we feeling? Does any of it make sense? Does all of it make sense? Does half of it make sense? How are we feeling with all the material from today? Which unit? Oh, okay. Yeah. Sorry, I was just trying to... some people were getting confused in the first lecture. They kept seeing the Coulomb C for the charge, and it wasn't completely clear that it was a unit and not a variable, so I started doing the light gray for the units when I'm remembering. Which I'm not very good at remembering right now, but just trying to clarify that a little bit more, especially when C starts to show up. I need to, so that the most useful part of it is that you use a calculator for it. Like there's a way to do it by hand that arguably is not at all better than just solving it using algebra. The reason that I stick with the algebra is because I like to do all of my things on the board and on paper. I typically don't use online calculators for anything that I do. But if there is a system. I think a lot of calculators have these. Wolfram Alpha has one, so I'm pulling up the Wolfram one, for example. So let's assume that you've got 4 equations. So if I had something like this, I would just plug in my equations as I had them. So call X, Y, and Z your currents, and then just have, so you've got to set them up like this. You've got to have them set it up like this in some sort of way, but it's like quite literally just plugging in these values. For example, if I plug this thing in, whatever they just had as their example thing, Wolfram thinks for a minute and then spits out those 4 quantities. And I'm not super upset if you use these. I think it's worthwhile to know how to solve these. But this is probably one of the easiest ways to do this one. Setting up the loop equations properly is going to be the most important part, and then looking at this and making sure that your answers actually make sense. Those are important details, I think. But it's essentially you're setting up inside of the equations, you've got every current you've got, and then the batteries, the potentials that you know would be on the equal side. And that's, yeah, modern solvers, that's all you need. I know there's some on like the TI-84 and the TI-89. Both of those have solving programs for these things as well. I'm not super concerned if you guys are using those. I'm more than happy to save yourself the work, honestly. It's one of the things that I don't ever completely understand. I remember my 3rd year of undergrad, I loved the quantum and the math methods courses that I took because when we were taking exams, we were split between take-home exams and in-person exams, but the in-person exams, it was wonderful because he would just sit at the front with Wolfram Alpha pulled up. And at any point you could say, hey, I need help with this integral. And he would plug it into Wolfram for you and boom, done. So, you know, I'm not super concerned if you're using Wolfram too, right? I appreciated it massively when I did it. It was a game changer for me. So since we're taking the course online and everything else, you know, go crazy. But I think with that, we'll close out the lecture for the day. Our last lecture before exam 3.